All right, so now we're going to discuss floating point arithmetic and basically what happens when you do sort of standard binary operations on floating point numbers and how the errors propagate basically. Okay, so let's say that we have y and z, okay, be exact values. And then y bar and z bar are the floating point approximations. Okay, and then by definition, as we've discussed, it's like with it's like with the notion of machine precision, what you have is that you have y bar is y 1 plus epsilon y, so that means more or less that it has a relative error of epsilon y, and then we have z bar is z 1 plus epsilon z. Okay, so I can also write it in terms of absolute error, in which case y bar is equal to y plus delta y, and z bar is z plus delta z. Okay, so this is the relative error representation. This is the absolute error representation. So we're going to see what happens, it's like to both of these, both the relative error and the absolute error, when we do standard operations on these numbers. So the first example of this is multiplication. Okay, so if I look at y bar, z bar, right, so this is, I'm going to write this in relative error as yz 1 plus epsilon, and I want to see how epsilon depends on epsilon y and epsilon z. Okay, so that's basically what happens. At the same time, I can also write this as yz plus delta, and again you can ask how delta depends on delta y and delta z. Okay, all right, so you can check that when you do this, okay, using this representation, this is obviously just y 1 plus epsilon y, z 1 plus epsilon z. So this is yz 1 plus epsilon y epsilon z. Sorry, 1 plus epsilon y plus epsilon z plus epsilon y epsilon z. Okay, and then what's going to happen is that we assume epsilon y and epsilon z are small, and so the product we're going to assume to be small as well. So I'm just going to ignore this quadratic term. So what that means is that when you do multiplication, then the relative error coefficients approximately just add. Okay, so I'm going to set this to 0. Okay, and you can sort of do something similar. It's like with the absolute errors, right? So y bar, z bar is y plus delta y, z plus delta z is y, z plus y delta z plus z delta y plus delta y delta z, and again I'm going to assume this is small, and so delta is going to be approximately y delta z plus z delta y, right? Okay, so hopefully you get to see, you get a sense as to what is going on here. Okay, so in any case, the take-home message here is that the relative error is small, in some sense, right? That if you start with small relative errors, the relative error of the product of two numbers, of two floating point numbers, is also going to stay small. But the absolute error is large if either y or z is large. Okay. All right. So that's the case for multiplication. Okay. So let's now look at what happens with division and then addition and subtraction. Okay. All right. Okay. So B is division. All right, so we want to do y bar divided by z bar, and we want to write this as y over z, 1 plus epsilon, or we want to write this as y over z plus delta. And then you can check that by the same kind of argument that epsilon is approximately epsilon y minus epsilon z, and then delta is approximately 1 over z squared z delta y minus y delta z. Okay, so the take-home message here is that the relative error is again small, but the absolute error is large if y is large, right? Or if z is small. In some sense. Okay? All right. And now let's look at what happens with addition and subtraction. Okay, so y bar plus minus z bar is y plus minus z, again multiplied by 1 plus epsilon, or you have y plus minus z plus delta. And here epsilon is approximately y epsilon y plus minus z epsilon z divided by y plus minus z. And delta is equal to delta y plus minus delta z. Okay, so the relative error, epsilon, is large if y is approximately z, or y is approximately equal to minus z. Okay. So when y is approximately z, the relative error is large for subtraction, and y approximately equals to minus z, the relative error is large for addition. Okay. So in general, what you shouldn't do is you shouldn't take the difference of two numbers which are nearly equal to each other. Okay. That results in a lot of error. Okay. So let me try to illustrate this with some examples. Okay, so there are two main situations to avoid. It's like when you're doing floating point arithmetic, in order to avoid large round-off numbers, errors. So two situations to avoid. Okay, so the first one is multiplication by large numbers. division by small numbers. Okay. The second situation is the subtraction of two nearly equal numbers. Okay, so this is what is called cancellation error. And this can result in a significant loss of significant digits. Okay. All right. So you might ask, well, how do you go about doing this? So what you can do oftentimes is that you can rewrite the expressions to avoid these two instances. So let me sort of just give you a few examples of what you can do. It's like in order to avoid these common round-off issues. Okay. So let's say I have some function f of x, which is x multiplied into the square root of x plus 1 minus the square root of x. Okay, and let's just see what happens, what goes wrong. Okay, so you have 6 digits. Let's say we have 6 digits of accuracy. Okay, so if you have f of 100, that's 100 times square root of 101 minus the square root of 100. Okay, so the square root of 100 is 10.0000123456, 6 digits of accuracy. And then square root of 101 is 10.0499. So f of 100, when sort of at every stage, at every operation, you sort of only retain 6 digits accuracy, is going to look like 4.99. So you have an error here of something like 2.44 times 10 to the minus 3. Okay, that's the absolute error. So basically what's happened is that, you've lost 3 significant digits, right? Because when you take this difference, only these 3 digits are significant. So we lost 3 significant digits. Okay. All right. So you might ask, well, how can I reformulate this to avoid, it's like this kind of subtraction or cancellation error? Okay. So let's see what happens. So I want to rewrite f of x is equal to x times square root of x plus 1 minus square root of x. So what you can do is you can multiply that expression, it's like with a quotient which is 1 in the following way. So if you take square root of x plus 1 plus the square root of x divided by square root of x plus 1 plus the square root of x, in principle you've not done anything to it. But when you expand this, what you get is just x multiplied into square root x plus 1 squared minus square root of x squared divided by a square root of x plus 1 plus square root of x. So that's going to be x over square root of x plus 1 plus the square root of x. Okay, so now you don't have the situation where you're taking the difference of 2 numbers which are very close to each other. So f of 100, for example, just becomes 100 divided by 10.0499 plus 10. So this is going to be approximately equal to 4.98756. And now my error is minus 6.06 times 10 to the minus 6. So you still have your full 6 digits of accuracy, which we started off with, right? So now we have 6. So we've kept your 6 digits of accuracy. So yeah, so it's important to be aware of these the potential for significant loss of accuracy and significant digits based on these kind of cancellation error phenomena. All right, and as this example demonstrates, oftentimes you can rewrite the expression to avoid this kind of cancellation error. Okay. All right. So let me just stop here for now.